move into speaking about the refractory periods. And the refractory periods are important in understanding why the action potential is all or nothing, and why they are always identical, and why they're always traveling in one direction, why they're unidirectional, okay? So there are two refractory periods. Okay, I see one question here, so let me address this. So someone is also asking about whether or not we could disrupt the action potential. So whether or not we can slow it down or speed it up. And the answer is we cannot slow down or speed up an action potential itself. We cannot change the quality of one action potential. What we can do is increase the frequency, how fast they're being fired or how slow they're being fired. So for example, this is how we appreciate different stimuli. So the difference between a really loud sound or a high-pitched sound and a low-pitched sound or a quiet sound are the difference in the frequency of action potentials. Another example that we'll look at in muscle when we get to skeletal muscle is if I'm lifting a very light object like a piece of paper, I'm going to be calling on maybe one or two neurons that are innervating that muscle. They're going to be firing action potentials at maybe a medium to intermediate rate. But if I am lifting something extremely heavy, I am going to be calling on more neurons, and they're going to be firing action potentials much more rapidly in order to appreciate the difference in that stimuli. So that's the way action potentials can communicate different types of stimuli and can have variation in terms of the outcome that's brought about, but an action potential in itself does not change. Okay, the way that we put them together can communicate different types of signals. Okay, that was a really good question, so thank you for those questions. All right, so we said that there are two refractory periods. And so kind of just going into the point that I was just making, action potentials can only increase their frequency to a certain point, right? Because we cannot fire an action potential while an action potential is going on. We also cannot fire another action potential immediately after one action potential has been completed, okay? And so there's a period there where the cell cannot be excited again, no matter how strong the subsequent stimuli is. And so there are two periods here. There's the absolute refractory period, and we talked about what contributes to this. This is the inactivation of sodium channels because of the closure of those voltage-gated sodium channels, specifically the inactivation gate on those channels. And because they remain closed until the membrane potential gets back to rest, we physically could not fire another action potential no matter how hard we tried. Okay, it's physically not possible. The duration of the absolute refractory period is pretty much the entire length of an action potential, which kind of makes sense, right? An action potential must come to an end for another action potential to begin. So the absolute refractory period is the period while an action potential is happening, we're not back down to rest. And so even if we have the strongest of stimuli, we could not fire another action potential just yet. Now, the relative refractory period is a little bit more laxed. This is because of the opening of potassium channels. So we still have potassium channels open. And so the membrane potential is still looking quite negative as potassium is still actively leaving the cell. And so here it's going to be harder to fire another action potential, but it's possible, okay? If we have a very strong stimuli that can kind of overcome or counteract the negative environment that we're experiencing here at about -85 or so, it's going to take a stronger stimuli, but we can fire an action potential, okay? So in other words, it's harder to depolarize a cell from -85 to +30 than it is to depolarize the cell from -70 to +30, but it's possible. It's just going to take a stronger stimuli. And so the relative refractory period is slightly longer. It's about a couple milliseconds after the actual ending of the action potential. And that relative refractory period is pretty much the duration of hyperpolarization. And so the cell is in its relative refractory period until we get right back to -70, where it's opening up of those inactivation gates on sodium, and all of the potassium channels have closed by this point. And so we start back from our resting state again. And so this is what keeps each action potential as a separate all or nothing event. We can't combine them because we cannot fire another one during one, and we cannot easily fire another one immediately after one has ended. Okay. And so the absolute refractory period prevents another action potential from being generated right away. It's because of the closure of the inactivation gates on sodium. And it's also what helps to keep the action potential going in one direction. So remember I talked about this kind of infectious nature of the action potential moving or propagating down the length of the axon. If I depolarize one segment of the axon and the adjacent segment becomes depolarized, the previous segment is now in its refractory period. And so the infectious nature of the action potential cannot be spread backwards because the previous segment of the axon is now in its refractory period, okay? And so that's kind of the importance of the absolute refractory period. The relative refractory period is pretty much the last part of repolarization and the extent of hyperpolarization. This is where it's harder to fire an action potential. And this is because sodium gates are closed and are inactivated. The inactivation gates are closed. So when we say that the gates are inactivated, this means that they're closed and incapable of opening, because although the activation gates may still be open, the inactivation gates are closed. Okay, and because that's kind of still wrapping up at this point, right? Remember, we had the closure initiated at +30, but it doesn't all happen at once. And so as we're still closing up some of these sodium gates, it's possible to fire another action potential, but harder.